All right. Welcome back to Advent of Code 2022. We've made it to day 19 now. I'm a little late on this video. I've been traveling and I just, could not brain after being awake for 24 hours. So catching up a little bit, but let's see if we can catch up. So let's take a look. Day 19, not enough minerals. Your scans show that the lava did indeed form obsidian. The wind has changed direction enough to stop sending lava droplets toward you, so you and the elephants exit the cave. As you do, you notice a collection of geodes around the pond. Perhaps you could use the obsidian to create some geode cracking robots and break them open. To collect the obsidian from the bottom of the pond, you will need waterproof obsidian collecting robots. Fortunately, there's an abundant amount of clay nearby that you can use to make them waterproof. Excuse me. In order to harvest the clay, you need special purpose clay collecting robots. To make any type of robot, you will need ore, which is also plentiful, but in the opposite direction from the clay. Collecting ore requires ore collecting robots with big drills. Fortunately, you have exactly one ore collecting robot in your pack that you can use to kickstart the whole operation. Each robot can collect one of its resource types per minute. It also takes 1 minute for the robot factory, also conveniently from your pack, to construct any type of robot, although it consumes the necessary resources available when construction begins. The robot factory has many blueprints, which is your puzzle input you can choose from, but once you've configured it with a blueprint, you can't change it. You'll need to work out which blueprint is best. For example, blueprint 1, each ore robot costs 4 ore, clay robot costs 2 ore, each obsidian robot costs 3 ore and 14 clay, and each geode robot costs 2 ore and 7 obsidian. And we have like a similar setup for blueprint number 2. These are not exactly what they look like in the input, but they're just made a little more readable this way. We'll go into that in more detail in a minute. The elephants are starting to look hungry, so you shouldn't take too long. You need to figure out which blueprint would maximize the number of open geodes after 24 minutes by figuring out which robots to build and when to build them. Using blueprint 1 in the example above, the largest number of geodes you could open in 24 minutes is 9. One way to achieve that is, and then it lists what happens in each minute of the 24. So it starts out by your 1 ore collecting robot collecting 1 ore, and then you have 1, collects another one, and now you have 2. Now that you have enough ore to build a clay collecting robot, you do so, and so on and so on. And eventually it ends up with 9 open geodes. However, by using blueprint number 2 in the example above, you could do even better. The largest number of geodes you could open in 24 minutes is 12. Now, determine the quality level of each blueprint by multiplying that blueprint's ID number with the largest number of geodes that can be opened in 24 minutes using that blueprint. In this example, the first blueprint has ID 1 and can open 9 geodes, so its quality level is 9. The second one has ID 2 and can open 12, so that's a quality level of 24. You add those up and you get 33. All right, and now we need to do the exact same thing for our input. And my input looks something like this. So there are 30 of them, 30 blueprints, and they look like this. So let's take a look. Okay, so as usual, we start out with I don't know if this is big enough for you to read it. Oh, let's do that. Okay. Yep, so as usual, we get all the lines from the file, and then we parse our blueprints. I copied a line from the input and turned that into a regular expression, replacing all the numbers or whatever it might be. In this case, they're all numbers. Replace those with these parenthesized \d, which is, as usual, digit. Plus means that there's one or more of them. And yep, just went through the whole thing, replaced them, and then I go through each line. I match every line against this regular expression right here and make sure that it matches. This is really handy so that if it didn't match, it would throw an exception, and then I could go in and figure out what I did wrong with my regular expression. And if it matches, then I turn them all into integers and into a tuple that I add to the list of blueprints and return the blueprints. Pretty simple stuff. All right. And then, as the puzzle states, you have to multiply the output or the maximum output from that using that given blueprint with the blueprint ID and add all those up, and that is our return value from part A. So, to make that happen, we create our solve function, which takes the blueprint and how much time is left. If we've run out of time, we are done, and that's it. This right here is a little bit of was a trick because I couldn't. I had some trouble with the scoping here, and just to make absolutely sure that things were behaving the way that I wanted them to, this is what I ended up doing. So by creating a dictionary like this, and it just has a single key, which is our answer, which we start out saying is -1, so that we have something to just a starting point. Obviously, we're going to find a better solution than -1. So I pass this dictionary in to our search function, and that means that that this is going to be the same dictionary. So it's the same dictionary. It's not a copy of it, and that this is how I could do pass by reference, basically. So we define the function and end up calling it with the state, which is our resources. So we start out with no resources and a single robot, which is the ore collecting robot. This would be the clay collecting robot, obsidian, and geode, and the time left. Cool. So let's go through it one step at a time. As we talked about, or as I mentioned a couple of days ago, there's a correspondence between the number of assertions that you'll find in my code and how much trouble I had getting there. This is definitely a symptom of me having some issues. So we start by defining the base case, which is just not doing anything at all. And not doing anything at all means that we will end up with as many resources as we have right now, plus however many geode producing robots we have, multiplied by how much time is left. And if that's better than the current best answer, then we store that and then we move on. I am going to skip over this next little bit because that's fun and it's mostly relevant for part B. So just skipping past that. Then we have a turns needed function, which takes the cost of a robot and works out how many turns it would take to generate one of those robots, if at all possible. So we define, we'll get back to the details of this function in a second. So we define all the costs of the different kinds of robots. Geode robot would cost, let's see, blueprint 5, the fifth element in our blueprint tuple is the geode, robot, ore costs. So how many units of ore building a geode cracking robot would cost. And how much obsidian it would cost as well. So these are so this is the index of the kind of resource that it corresponds to, and then we have a tuple that defines the costs in ore, clay, obsidian, and geode. So obviously nothing costs geode because geodes are what we're collecting, but it's a lot easier if these tuples always have 4 elements and they're always the same thing: ore, clay, obsidian, and geode. So we define the cost of all these different kinds of robots, and then we we go through each of them, and if the number of robots that we already have of this specific kind is more than the maximum cost of this resource, so whichever robot costs the most of this specific kind of resource, that means that even if we didn't build any more, we would always have enough of this kind of resource, because we can only build 1 robot in each turn or for each minute. And if we have more robots producing that kind than any of them needs, that means there's no point in trying to see what would happen if we build more robots of this kind, because we'll never need them. This does not apply to the geode producing robots, obviously, because those are the ones that we are trying to maximize. Then we calculate the how many turns are needed for this specific kind of robot. So we take the robot costs, which again is one of these 4 tuples with ore, clay, obsidian, geode in order. So we pass that in, and we pass references to our resources and robots. So our current state, how many of each kind of robot and each kind of resource that we currently have, we pass that in. We zip those lists together. I don't remember if we talked about this, but essentially what this does is it iterates through each of these lists, and one at a time returns the first element of each list, then the second element of each list, and so on, and returns them as tuples, so we can unpack them here, which gives us resource count, robot count, and the costs to build the kind of robot that we're considering. If we have enough of the resources, if we have more resources than this particular kind of robot costs, then to gain enough resources of this kind, we need 0 turns, right? Because we already have them. The other simple case is if we don't have any robots at all of this kind, then I just return 10,000, because that's bound to be more time than we have left, and we just need to make sure that our calling function knows that trying to build this kind of robot is going to take us effectively infinite time, because we don't have enough time to do it. And then finally, the case here that we want to look at is the one that actually makes any sense. So we have the cost minus how many we currently have. Then we also have to consider how many that we would be generating at this for each round. And we divide it by how many robots we have of this kind. And to make sure that we don't try to generate, let me see how I can explain this the best. So suppose we have 2 robots and no resources, and it costs 2. That means that it is going to take us 1 minute to do this. So let's try filling those details in just for funsies. Okay, so suppose we have 2 robots and it costs 2, and we currently have, no, let's say it costs 3. We have 1 resource and we have 2 robots. Okay, so 2 plus 3 minus 1. So that's 4. And divide by robot, how many robots we have. So that would give us 2 turns, but 1 turn is really is going to be enough, because that gets us above the number. So we subtract the 1 to make sure that we would, in that case, we would only get the right amount, right? Okay. And then at the end of it, we return the maximum of the turns. Each element in turns tells us how many turns we would need to go through to get enough of that specific kind of resource. And obviously, whichever one takes the longest is the one that matters. That's the one that tells us how many turns we actually need to go through this. So T is how many turns are needed, and if that's less than how much time we have left, then we're good to go. Then we can go for it. And to do that, we create a copy of the list of robots, and we increment the specific type by 1. Okay, so this next bit is a little fiddly. The number of assertions that you see in my code, and the number of comments, and how spelled out things are is a very clear indication that this was tricky. So that's what we're seeing right here. So we take the time plus 1 because we're still in the middle of this current turn, and this turn is going to generate this kind of resource as well. So we know that basically at this point we've decided that we want to try to generate one of these kinds of robots, and that's going to take us T minutes to do so. And in that time, all the existing robots are going to be generating stuff as well. And this multiply vector by scalar basically does, if you have like a vector like that and you multiply by, say 3, the output is going to be 3, 6, 9, 12. Make sense? Hope so. So that is what the current set of robots would generate. Then we add what we already had when we started. Add vectors just adds each element of the vectors with the others. And finally, we subtract what it would cost to build a specific robot. I didn't make a subtraction function. I just add the inverted vector like this. Don't worry too much about them being called vectors if that confuses you. They're just sets of numbers. We're not doing any fancy vector stuff. I started out calling them vectors because I thought I would need to use NumPy, and NumPy kind of, I thought it would make sense to help to call them vectors, but it did not. So here we are. And we end up having calculated how many resources that we would have at that time. And we pass that into our search function along with the new sets of robots, and we subtract the time that it would spend, as well as the time that we spent this current minute, and we keep going. And eventually we end up with an answer, and we return, and we're done. And that gave us our right answer for the first one. Now, part 2 was... part 2 was tricky. Let's take a look here. Okay, part 2. While you were choosing the best blueprint, the elephants found some food on their own, so you're not in quite as much of a hurry. You figure you probably have 32 minutes before the wind changes direction again, and you'll need to get out of range of the erupting volcano. Unfortunately, one of the elephants ate most of your blueprint list. Now only the first 3 blueprints in your list are intact. In 32 minutes, the largest number of geodes blueprint 1 from the example above can open is 56. And one way to achieve that is, and then it has like this whole list of what happens each minute. Okay. However, blueprint 2 from the example above is still better. Using it, the largest number of geodes you could open in 32 minutes is 62. You no longer have enough blueprints to worry about quality levels. Instead, for each of the first 3 blueprints, determine the largest number of geodes you could open. Then multiply these 3 values together. Don't worry about quality levels. Instead, just determine the largest number of geodes you could open using each of the first 3 blueprints. What do you get if you multiply these numbers together? And let's see. Part B looks very similar to part A up here. We get the lines, we parse it out, and we start with, because we're multiplying, we start with a return value of 1 so that we can multiply the others to it. And then we only want to go through the first 3 blueprints, and that's what we're doing right here. And then we multiply the answer to RV and end up returning it. And I'm not sure why I didn't look at exactly what was going on, but by accident I ran this code. Usually I try to run it against the sample input first so that I can make sure that I get the right responses out, and then before I kind of try to solve it for the real problem, because that usually takes a lot longer. And if I can't even solve the sample in like a reasonable amount of time, what are the odds that I can solve the real input? And up until I finished this one, I would have said that those odds were 0. I now know that that's not the case, because strangely, the solution I already had gave me an answer to the real problem in a reasonable amount of time. Trying to do it on the sample input, I don't know how long that would have taken, but I just gave up waiting for it at some point because it was stupid. But yeah, by accident I ran it against the real input, and I got my answer in, I don't remember. We can try again, actually. But yeah, that was before I added this little optimization here. So you can just load the pop. I do. So this is going through all the problems now. Oh, no, that's not going to work because I'm trying to do that sample again, and that's really, so check this out. Gonna run it against against the real input. And after a little while, we get an answer. Super exciting watching this, huh? Bum, 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 bum. I don't think we want to wait for that. But it was, a perfectly reasonable amount of time. I mean, longer than usually it takes. If you have like the actual, like the best solution for it, because we've talked about this before, that usually the best solution is, almost instant, right? Once you've found out, the optimizations and different, tricks and whatever, then it's usually, very, very, very fast. Dun, 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 dun. So 11, 18, 12. Yeah, give it another little bit of time. But yeah, the interesting thing is when I run it against the sample, I'm not sure how long it's going to take because I gave up waiting for it. But I did get my right answer for the real input, which for me was 3510. But yeah, it didn't work for the sample in like any reasonable amount of time, and it's not because the sample only has two blueprints, because this takes up to like the third if there is three. See, that took a couple of minutes, but for the sample, I don't know, man. It took a long time. So the optimization that I added was trying to identify an upper bound on how good of a solution we could get based on where we currently are. So suppose we are looking at this graph that it effectively is, right? And we have we've managed to create 4 geodes or whatever, right? And we pretend that somehow we have 3 minutes left and we have like 3 geodes. So in those 3 minutes, if we've already worked out how much we would get if we just hung out, like didn't do anything and just hung out. That's what we get here. If we somehow found a way to generate a new geode robot now, and each minute until we run out of time, in addition to what we're already generating with what we have, in the next minute we would get 1 additional geode because we have somehow managed to create an additional geode robot right now. So we get 1 more. The minute after that we get 2 more. And the minute after that we get 3 more, because we have like an increasing number of geode producing robots. And the sum total of that is you can rewrite that to n times n plus 1 divided by 2. Doing a sum of a range and whatever would have been fast enough too. This just felt better. And then we compare like the total of if we were just hanging out and not doing anything with this imaginary magical situation where we've managed to generate a new geode producing robot every minute. And if that is still worse than the answer we've already found, then there's no point in trying to consider what are we going to spend the rest of our time on? What kind of robots are we going to be generating? Because obviously it's not going to get any better than this, optimal case. And yep, adding that little bit of optimization. Oh yeah, it's so fast that printing all those things is just adds a lot of no. Oh, where is it? There it is. That's not how you spell pound. There you go. Doop-a-doop-a-doop. Ba-doop-a-doop. There we go. That's it. So with that little optimization, it's actually pretty fast. Yeah, I think that's pretty much it for day 19. Let's see if there's anything that we haven't talked about. No. Yeah, here are my vector functions. They're not particularly interesting. But yeah, I think that was it. It was time consuming. We talked about how the leaderboard and the first 100 people on the leaderboard, how long time they spend on it is a really good indicator for how complex a problem is, or how how much time you can expect to spend on it. If you usually spend twice the amount of time on it, then you're probably gonna spend twice the amount of time of the number 100 on the list tomorrow as well, and so on and so on. And once again, the leaderboard for this particular one has, let's see, I think number 100 spent like an hour on it. Yeah, very close to an hour. And I spent, I don't know, 3 hours on it. And then after I finished it, I looked at other solutions to get some, just to see if there was anything better that I could share with you guys today. So I did some restructuring based on what I found, because some of these people who solved this, they had some really elegant stuff that helped a lot. But that's all we have for today. I hope you could use it. And if you have any questions or comments, you leave them below. Otherwise, you like and subscribe, and I will see you tomorrow or tonight. Or, well, actually, I'm a day behind, so I'll see you in a little bit when I'm done with day 20. All right, bye.